ones are 20% for I, 30% for A, and 30% for E. Okay, then the next step would be that we don't have to order them. These are already in order. What do you do with a tie? Well, it doesn't really matter. What you might do in this case is make the smaller tree go on the left. Okay, so this is a smaller tree than that, so let's put it on the left. Or you might decide to go in alphabetical order with the leftmost leaf here versus the leftmost leaf of that one. It really doesn't matter as long as there's some rule. Let's leave it like this as it is. So we put these two together. 20 plus 20 is now 40%. And we have a tree whose left part is the CT and whose right part is the I. Now we have 30% for A, and the B is 30%. Okay, now we do have to put these into order, so the next step would be keep these two the same. A at 30%, B at 30%, and then 40% for... I've never really figured out an easy methodical method for doing these when you're writing them out by hand, except for doing the actual physical rearranging of things. Okay, so 30, 30, 40, these are two the smallest, so let's put them together. So they now form a new tree with 60% with A and E there. And you notice that this one's 40% versus 60%, so we may as well put it over here. So that the smaller of the two goes on the left, and now the final step would be that we put the two together. So the left tree and the right subtree. The left subtree is all of that. So CTI. The right subtree is all of this. So A and E. And we label them left branch 0, right branch 1, left 0, right 1, 0, 1, 0, 1. And so now, if we go in alphabetical order, A, C, E, I, T, A is 1, 0, C is 0, 0, 0, E is 1, 1. I is 0, 1. And T is 0, 0, 1. Okay. And thankfully, we get this code. And the other point about it is that there are other equivalent answers, so there are other possibilities. So you would have gotten slightly different things if instead of having A and E in this order, you had B and A. So that would have been swapped around. So E would have been here and A would have been there. So in that case, A would have been 1, 1 and E would have been 1, 0. So that would have been an equivalent code. Okay, let's see. So the point about all this is that, just like here, the most frequent ones, or the two most frequent ones, so in this case, what were the two most frequent, A and E, effectively end up with 2 bits and are the shortest. So A and E end up being shortest. I is also the same length, even though it's a little bit less frequent. So the intention about the whole thing is that more frequent characters get fewer bits to encode them, whereas the less frequent characters get more bits to encode them. And so because the more frequent characters have fewer bits, you've got a total savings. Right. And again, so if you want to encode the word CITE, then you say 000, I is 01, T is 001, and E is 11. And this particular code is actually unique because the person who receives it at the other end, he starts reading it and you say, is there a character for 0? No, there isn't. Is there a 00? No, there isn't. Is there a 000? Yes, there is. That ends up being C. Then you look at this and say, is there a 0? No. Is there a 01? Yes, there it is. So that's I. Is there a 0? No. Is there a 00? No. Is there a 001? Yes. So that's a T. And then, is there a 1? No. Is there a 11? Yes. You get that? Oh, as I said last time, I think this is really rather an amazing sort of code that you don't even have to tell where the breaks are between letters, even though there are variable lengths for each of the codes. So 3 bits, 2 bits, 2 bits, 3, 2, 3, 2. You don't have to put spaces or anything. You can just send the whole thing as a string of bits. If you wanted to put spaces, in your words, where you just count space as another character in your set, so something like this. T's might make up 5% of the thing, and a space or an empty character might take up 5%. So you just treat the space as another character, which I think is what happens in this one. So in this particular one, AEIST, and then space as a character, and an L for new line. Character. So maybe I could just let you go on this one for a little while, and if you could also figure out what the compression rate of that is. Actually, I've already given you the answer, but okay. I'll let you go on it and see if you can reconstruct the actual Huffman code, and then we'll just have a look at the last little bit. So if I give you, say, 5 minutes for it. Okay, I'll just give you another minute on that one. Okay, I won't go through the construction of it, but what I will do is just say, just here is the tree as I've reconstructed it. So we've got 1, 2, 3, 4, 5 levels from the root. So all the different characters appear at the leaves, and then if you order the characters according to the count. Now, the only tricky thing here is that the message, so the implication here is that there is a message of 59 characters, and each character occurs this many times. So this isn't the relative frequency as in the percentage. This is actually just the count of the characters in the message. So E occurs 15 times, space occurs 13 times, I occurs 12 times, new line occurs once. And you don't have to put this into a percentage, because all you're really interested in is, relatively speaking, which are more frequent than others. And regardless of whether you do a percentage, E is the most frequent, space is the next most frequent. So on the end, you get this structure. And the thing to see is that E, space, and I are at the highest, the closest to the root, each 0, 0, 0, 1, and 1, 0, each taking the smallest number of bits. Okay, A is next, on the next level down, with 3 bits. Next level down, T, using 1, 2, 3, 4 bits, one there. And then S and U line are on the very bottom, furthest away from the root. So the greatest number of bits, 1, 2, 3, 4, 5 bits each. What you do notice here, it's worth pointing out that you'll never have characters that are on this first level with just 1 bit in their code word. You've always got to have at least 2 bits. Why is that? Well, remember what the definition of the code is, or the definition of a prefix code is that no code is at the beginning. So no code, where are we? No code forms the beginning of any other code. So if we look through here, 1, 0 is not at the beginning of any of these. Okay, 0, 0 is not at the beginning. 1, 1, 1 is not at the beginning. Almost, it's 1, 1, 0, but it's not 1, 1, 1. 0, 1 is not at the beginning of any code. So no code appears as the prefix of any other code. So that automatically means that you can't have 0. No, that's not quite right. You could have 0. I've just told a lie. So I suppose you could have a code which looks like 0, 1, 0, and 1, 1. If you had 3 characters. So if you've got 3 characters, then you could code them up like that, from most frequent to least frequent. So my mistake. So 0 doesn't appear at the beginning. But as soon as you've got more than 4 characters, or 4 or more characters, you're going to have at least 2 bits in them. Okay. Then finally, what's the best possible fixed length code? So we have 1, 2, 3, 4, 5, 6, 7 characters. So 7 characters. What's the shortest number of bits if we're going to have fixed length? Okay. Well, we can't have 2 bits, because 2 bits for each character means we can only have 4 characters. So on the end, we need 3 bits. So we do the usual thing, just counting in binary. So 3 bits would give you the possibility of 8 characters. And since we've only got 7 characters, 3 bits is enough. So that's why the best possible fixed length code is of length 3. So if we were going to use A, B, I, all the way down to new line, and leave this one as redundant. So if these were our characters with the 3-bit codes for each character, and we've sent 59 characters, then in total you'd have 3 bits per character, gives you 177. And I've crossed out characters, you've got 177 bits in your string. With the Huffman code, what you do is you say let's see, how many bits is each one? So I, space, and E all use 3 bits. I, space, and E. A uses 4 bits. T uses 1, 2, 3. Sorry, I can't count today. 2 bits, 2 bits, 2 bits. 0, 0, 0, 1, 1, 1. Oh, sorry, 1, 0. 3 bits for A. 4 bits for T and 5 bits for both S and new line. Also can't write, so that's number of bits. So we just calculate up. Out of the 59 characters, 10 of them are A. Okay, so A. We've got 10 lots of A, so we need 30 bits altogether. 15 of them are E's, so we need 30 bits altogether. 12 bits are I, so 12 bits are I, so we need 12 twos, 24 bits for all those. What's next? S is 3, so 3. S needs 5 characters, so 3 times 5. T, there are 5 T's in the message, and each one requires 4 bits, so 5 times 4 is 20. There are 13 spaces. Spaces are worth 2 bits, so 13 twos are 26. And finally, there's just 1 new line character, and the new line character takes 5 bits. Okay, so 15 twos, 3 twos, 12 twos, 10 threes, 5 fours, 3 fives, 1 5. Add it all up together and you end up with 155 bits, which is compressed compared to the 177 that you would normally have to do if each character got 3 bits. So how much have you saved? Well, 177 minus 150. 177 minus 150 is equal to 27. Okay, so 27 out of the best possible fixed length, 177, is 15%. So basically, we've saved 15% by compressing these more frequent characters into 2 bits rather than using 3 bits, at the expense of the less common characters using more than 3 bits. But this is outweighed by the compression in using the most frequent characters using only 2 bits rather than 3. So the compression rate is 15% because that's basically how much you're saving, how much you can squeeze. The other way of reading it is that the Huffman code is 15% shorter than the best possible fixed length code. Right, that more or less ends the lesson. I don't think there's much more I can say about Huffman codes. In fact, I think we got down to 6 of 6, so that really is the finish. Okay, well, we could probably have an early mark, unless there's any questions that anybody would like to ask. Yes, no, indifferent? Yep. Joshua says no. Thumbs up for no. Nobody else? Okay. I'll send out another email about the test tomorrow just to remind you. So in particular, if you find that you can't get a quiet space or the internet has dropped out at 5 to 10 or even between 10 and 11, just let me know and we'll organise a different time. But otherwise, just turn up to the LMS site tomorrow at 10 o'clock, ready to do your test. You should get it done in less than 50 minutes, but I'll give it a full, let's say 50 minutes, 55 minutes, till a few minutes to 11.
So will we just see the link, click on it at 10 o'clock and then
yes, yep.
Go through for an hour? Yep.
So okay. I'll open it up at 10 o'clock. Make sure everybody's here first, open it up at 10 o'clock then. So you can zoom, let's see. I was going to say, is there a necessity to zoom in? I don't think so. So there's no necessity to zoom. You can just flick me an email if you have to.